Okay, let's do a couple examples. We're going to look at two different series and determine whether they converge. Now remember I told you that the integral test is kind of my last resort. So I'm going to try the other tests that we have so far and see if I can avoid the integral test if possible. So first things first, I'm going to try the nth term test. The nth term test says that we need to look at the limit of the parent sequence to determine if this approaches something other than 0. But I can see as n approaches infinity, I end up with n over n squared, so that n squared in the denominator is growing significantly faster, so this approaches 0. Inconclusive. We don't know if this will approach 0 fast enough. Okay, so let's try the ratio test. The ratio test then says to find the limit as n approaches infinity of the next term, so this is n plus 1 over n plus 1 squared plus 1 divided by the previous term. So I'm going to flip and multiply the denominator. Okay, if I do this, then I will see that, and this has to be less than 1 in order for this to be true. This is the ratio test, and it's like R, it's like that geometric series. If this ratio is less than 1, then we know that this will be converging. Okay, so I'm going to try this then. Let's see, if I do a bunch of multiplication in the top, because remember, we're looking at the limit as n approaches infinity. I'm not seeing anything that will cancel. The plus 1s will not cancel. So there's nothing that's going to cancel here. But if I do some simplifying, and I'm going to be lazy here, if I do multiply the numerators together, I'll end up with n cubed plus something, something, something. Some n squared terms, and so on and so forth. If I multiply the denominators, I'm going to get the same thing because n plus 1 squared is n squared times the other n is also some form of n cubed. And as n approaches infinity, the only thing that really matters in this case is that highest degree term. So the only thing that really matters in this case is the n cubed. And n cubed over n cubed is just 1. So unfortunately, the ratio test is also inconclusive because this was not less than 1 and it was not greater than 1. It was equal to 1. So we don't know if this converges or diverges based on either of those two tests. So as our last resort, I'm going to find the antiderivative. So I'm going to integrate from 1 to infinity, x over x squared plus 1. Let's be proper about this and write this improper integral from 1 to b. Okay, so let's see. This looks like it might be in the form. Actually, I'm going to let you try. Go try and integrate that, please. I'm going to stop. Okay, I hope you tried. This is in the form, I think, of u prime over u. If I let u equal x squared plus 1, u prime is 2x, so I'll write a 1/2 out in front. This is u prime then, and that's u. So we've got the limit as b approaches infinity of 1/2 the natural log of x squared plus 1, evaluating that from 1 to b. So I end up with if I replace x with b, I end up with the natural log of b squared plus 1 minus the natural log of 1 squared plus 1. As b approaches infinity, I know that this natural log approaches infinity as well. So this is infinite. Doesn't even matter what this is equal to. This is approaching infinity, which means that this antiderivative is diverging, therefore the series diverges. So here's how we rewrite the answer. We say that this sum from 1 to infinity of n over n squared plus 1 diverges by the integral test. I messed up in that I didn't go through the process of showing that this was all positive and certainly decreasing. But let's look at that really quickly now, because that's something you have to check before you can just jump into this integral test. So first of all, we know that all terms are positive because n starts with 1 and the numerator is n, so always positive. The denominator is squared plus 1, always positive. So already we can see that this is a positive series. Next thing, we need to make sure that the terms are getting smaller and smaller, and we can say that that is true because we have n over n squared. And since n squared is significantly larger than n, we know that each term is decreasing. But we've got to check that every time before we just jump right into this, the integral test. All right, let's go to the second example. We have 1 over n squared plus 1. I'm just going to jump into the integral test, but let's just make sure this is going to work. First of all of these terms are positive because we're starting with n equals 0, and if we square that, it's positive plus 1, still positive. So this is definitely a positive series. And I can see that the denominator is getting significantly larger than the numerator, so we know that these terms are also decreasing. We know then that the integral test will apply here, so let's jump into it. I'm going to skip a step and just say we're going to go straight from 0 to infinity, 1 over x squared plus 1. This is one that you've been seeing a little bit more in this unit, and hopefully you're starting to recognize it, especially maybe if I write it this way. 1 plus x squared. Hopefully you're starting to recognize that now as arctangent. The antiderivative of 1 over 1 plus x squared is the arctangent of x from 0 to infinity. Oops, I didn't replace my b. I will do it now. From 0 to b. All right, let's now use the first part of the fundamental theorem, arctangent b minus arctangent 0. Okay, remember arctangent is saying which angle will give us this output. So in the first case, we're saying on which angle is the is tangent going to equal infinity? Because as b approaches infinity, so when will tangent equal infinity? That happens when b is pi over 2. So this whole thing becomes pi over 2. Not b. Shoot, I used the wrong angle. What angle are we equaling b, which is infinity? You knew what I meant. So anyway, so we know that tangent will equal infinity at the angle pi over 2. At which angle will tangent equal 0? Tangent is equal to 0 at 0. Oh, sorry about that. I got my things mixed up. So we know that this integral converges because we got a constant value. Therefore, the sum will also converge. So we'd say the sum of 1 over n squared plus 1 converges by the integral test. Okay, one more test, and this one is actually a really nice one. This one comes up a lot, and it's called the p-series test. Now it's really, really important on the p-series test. It can only be written in this form. 1 over n to some value p. So like 1 over n squared. 1 over n to the first. 1 over the square root of n would be 1 over n to the 1/2. So the p-series is pretty specific, but it's going to come up a lot because it's really kind of nice. So what I want you to think about is, in what situation would a p-series converge? What would p have to be equal to in order to make every p-series converge? So we've looked at a couple examples. 1 over n, we know that this diverges. So in this case, p is equal to 1. We looked at the other n equals 1 to infinity of 1 over n squared. We knew that this one would converge, and p is 2. So what about in situations like 1 over the square root of n, where p is 1/2? What about if p gets even larger? What about if we have n to the third? And what about n to the -2? Go explore this just for a few minutes. Use the integral test because it's a pretty nice one to use to check these. It's just power rule. So go use the integral test and determine which of these converge, which diverge. Okay, welcome back. Let's take a look. I'm going to use the integral test on each of these three and see what we can figure out. So 1 over the square root of n. This is from 1 to infinity of n to the -1/2. So if I find the antiderivative, that should be an x, not an n. If I find the antiderivative, I add 1 to that, which is 1/2, and then divide by 1/2. So the antiderivative is 2 times x to the 1/2. So already I can see that when I plug in 1 and infinity, or 1 and b approaching infinity, this is going to be something very large. So I have 2 times the square root of b minus 2 times the square root of 1, and as b approaches infinity, this is going to approach infinity. So we know that this diverges. I didn't leave myself enough space. What about 1 over n cubed? So if I find the antiderivative, the limit as b approaches infinity, let's see if I can write it right the first time all the way through 1 over x cubed dx. If I rewrite that, then this is x to the -3. Add 1 to that exponent, and that's still a negative exponent. So that's x to the -2. This is then 1 over x squared is the antiderivative. And I know that if I plug infinity into 1 over x squared, that's going to become 0. So that means this will converge. This one I don't even really need to do anything with it because I know that if I rewrite 1 over n to the -2 with a positive exponent, it becomes just x squared. And of course, when I find the antiderivative of that, 1/3 x cubed, and I evaluate that at infinity, this is going to be infinitely large. So this also diverges. So I hope based on this, you can see that there's only a certain number of values for p that will make a p-series converge. If n is equal to 1, diverges. If n is greater than 1, converges, converges. Anything less than that, we diverge. Okay, so a p-series converges if and only if p is greater than 1.